Okay, so I actually did not mean to cut that video off so short, but anyway, so this is video 4. Yes, this is video 4. Now, hopefully the last one, I just want to make sure I cover everything with sequences, and so on Monday, we're going to move on to series. Okay. So this last example, and again, we're determining whether the sequence is bounded, so we have to check whether it's bounded above and below. And so again, we're going to look at some terms. And you don't always have to do this, but it's just nice to look to see what's going on with the terms. And here we have n is started from 1 again. So we have the first term will be 1/2, and then we'll have 4/3, and then we'll have 9/4, and then we'll have 16/5, and so on. Okay, so our values are increasing, it looks like, but 1/2, so since our values are increasing, 1/2 still will bound it below. So it's bounded below by 1/2, or 0, or any number less than that. So in this case, it is bounded by any number less than 1/2 since the values are increasing. So bounded below by 1/2. Okay. And we're going to check to see if it's bounded above. Alright, and so we're going to take the limit as n goes to infinity of n squared over n plus 1. And again, I'm going to treat this as a function and use, since I'm treating it as a function, and since it's a rational function of polynomials, I'm going to use the properties that we learned from Calc 1, where it states that if you have a rational function of polynomials, let me see, and if the degree of the numerator is larger than the degree of the denominator, then that function, that rational function, diverges. Okay. And again, too, you can use L'Hopital as well to solve to see that it's going to diverge. And this tells us that it's not bounded above because no number stops it. So it's not bounded above. All right. And also, although it's bounded below, in order for the sequence to be bounded, it has to be bounded below and above. So be careful, it has to do both. And so therefore, the sequence C sub n is unbounded. Okay. All right. So now I want to give you some definitions and some theorems that will be very useful. And the first, let's call this theorem 1. And you sort of already know it because it's what we've been doing. If the sequence A sub n converges, then A sub n is bounded. Okay. So what this is saying, if you know you have a sequence and you know that it converges, then you can say it's bounded. If you have a sequence, and this is, I don't know, for those math majors who have to take foundations, proofwriting, if the sequence does not converge, that doesn't mean it's unbounded. That means you need to do more work to determine whether it's bounded or unbounded. Okay, so this only states if you have a sequence that you know converges, then you know that sequence is also bounded. Okay, and I want to now give you a couple definitions that will be useful. All right, and the first one, started here, is the sequence A sub n is increasing if A sub n is less than A sub n plus 1 for all n. Okay, and so an example, because I like to give examples, so hopefully it'll make the definitions make more sense. And I'll keep it simple. So an example of an increasing sequence would be 1, 2, 3, 4, ... Okay. So notice too, and I want you to make sure you note that there's no equal sign here. So the values have to be, for it to be increasing, it has to be, as you go up in your indices, the value should increase. So this right here is an example of an increasing sequence for every n. Okay. Let's see. A sub n. I really don't like these squiggles ones. I'm sorry. I'm talking to myself now. A sub n is decreasing if a sub n is greater than, strictly greater than, a sub n plus 1 for all n. Okay. And so an example of a decreasing sequence would be 1, 1/2, 1/3, 1/4, ... So that is a decreasing sequence. All right, and star, a sub n is called, and actually, I'm sorry, let's make this a definition. I don't want to make it a star. Definition. And I want to change colors because I'm tired of this. Okay. A sub n is called monotonic if it is either increasing or decreasing. Okay, it can't do both. It's either one or the other. All right. So the sequence is monotonic if it's either increasing or decreasing. So the above examples I gave you, those were examples of monotonic sequences. All right. And theorem 2, so another theorem. This theorem states a bounded monotonic sequence converges. All right, so if you have a sequence that's bounded, which means, of course, it's bounded above and bounded below, and monotonic, which means it's either increasing or decreasing, then that sequence converges. So your homework is to use theorem 2, or let me restate this. Sorry. Using, hope you're writing with a pencil, using theorem 2 state whether the sequence converges or diverges by determining, I'm sorry, this is not going to fit on one page, by determining if the sequence is bounded and monotonic. All right, so you're going to, for each of the problems I give you, you're going to tell me, using that theorem too, if it's bounded and monotonic. And so if it's bounded and monotonic, so if you show that it's bounded and monotonic, then that means your sequence converges. If one doesn't happen, then it doesn't converge. Okay, so the first one is a sub n equals 1 over n. 2. So you might already know of these sequences by just taking the limit, but I want you to use this theorem to show. So tell me what's bounded and above, what's bounded and below, if it's bounded, and if it's monotonic. So if it's strictly if it's increasing or decreasing. Okay, so a sub n is 1 over n, 2 b sub n is n squared over n plus 1, and 3, and let's say all these starts from 1 to infinity, just to keep it simple. 3 c sub n equals negative 1 to the n, and then goes from 1 to infinity. Alright, so this will be due on Thursday by 5 p.m., and I will set it up on Moodle. Alright, take care.